Okay, well, last time we discussed the model that we had developed here. We mentioned that it's consistent with the local geology, what the geologist has obtained from other water wells in the area, the test borehole with a resistivity log, and so on. We also mentioned that as geophysicists often do, we mentioned that the solutions that we obtain are non-unique, that there could be, variations, even when you constrain the model as best as you can using available geological information. There's still some variance in possible solutions that have, roughly the same amount of error. So you can see the calculated apparent conductivities here coincide pretty well with the observations, but not exactly. So there's a small amount of residual error that's left in the data, and all of these solutions over here are consistent, provide similar levels of error. And so when we look at this, we see that the contaminated portion of the aquifer could extend from about 7.5 to 10.5 meters in thickness. The depth of the upper part of the aquifer is constrained, right? So we know that it's located at 10 meters beneath the surface. The base, we don't really know. We didn't really know whether it would be contaminated or not. The models indicate that, okay, you've got a problem. You actually have some contamination in here, and it could extend from 10 meters down, 7.5 meters into the aquifer, 10.5 meters into the aquifer. We also see that the uncontaminated aquifer could extend down to depths of between about 23 to 45 meters. This would be the depth to the top of the sill. So this kind of variability, if you were going to talk to whoever it was that hired you, the community or some contractor, maybe the company itself that's managing the wastewater lagoon, doesn't want it to be a problem, you would want to report back that there's some ambiguity in your results. The contaminated zone could be somewhere between 7.5 to 10.5 meters in thickness. But one thing that we do know, the model is misleading in a sense, indicating that, well, the depth to the base of the aquifer could be between 23 and 45 meters in depth, when we know it should be around 30 meters. So the results are very informative, and I think one of the other things that you can notice that we haven't really talked about the numbers, but you can see that there's a greater range of possible thicknesses in the lower conductivity freshwater zone than there is in the higher conductivity contaminated zone. And the reason for that is that, well, if we have a high conductivity layer, particularly one that's closer to the surface, if we vary the thickness of that layer, it's going to have a greater influence on the apparent conductivities than a lower conductivity layer. So there's kind of a balance between the thickness of this layer and its conductivity. Having such a high conductivity, it has a significant influence. So we only need to vary it a little bit in order to produce significant changes in error here. Whereas for this underlying freshwater zone, we can vary its thickness quite a bit and still remain in that same level of error. So if you wanted to illustrate this graphically for this particular sounding, if we were presenting it in cross-section form, we'd want to indicate, well, the conductivities all the way across here for the near-surface clay are about 50 millimoles per meter. The contaminated zone is around 100 mos or millisiemens per meter. But it could extend from a depth of about 7, the base of the contaminated zone could be anywhere from about 17.1 meters to 20.6, so we've got this range of variability here, while the freshwater zone could extend from 23 meters down, the base of the freshwater zone could extend from 23 meters down to 43 meters. We know that it's located here at about 30 meters. So we pretty much have to honor the geological background information and put the top of the silt in here around 30 meters beneath the surface. So, as we've emphasized in this, as we've gone through this model development activity, and here we've changed the conductivities around so that they fit the expectations that we have based on the background data. We see that we have a contaminated zone, which is about 9.8 meters in this case, after an additional inversion. And the base of the aquifer is located at 30 meters, consistent with the geological data. This would be our final model. We wouldn't want to lose sight of the equivalent solutions there in our presentation of results, but this would be a result that we might plot up in the model here. So one of potentially several, but one that honors the geological background data at the site. So base of the contaminated zone, so we have a contaminated zone which is about 9.8 meters thick in this case, and freshwater zone which is about 10.2 meters thick in this case, base of the freshwater zone, top of the silt, where it should be down around 30 meters. Okay, so if we go through the modeling exercise, we have these soundings. We already know what the result is here for the first sounding, because we have a geophysical log there. Not to get too far into this, but there could be contamination in the vicinity, so that the results of the modeling of the sounding might not actually match what we see in the resistivity log. But that's another issue, but you should keep that in mind. Depth to the base of the aquifer is constrained by local geological mapping. How are the contaminants distributed across the profile? The main question that we have. And question is, that we've already addressed really, can we keep the base of the aquifer at about 30 meters? And we've already shown that you can restrict aquifer thickness to 20 meters without increasing error. So we can honor all these constraints, and we can get to a final solution of what the distribution of contaminants are, or what the distribution of the contamination zone is across this profile by going through this modeling process. So it's very useful. It's really useful, and particularly when you use all available geological background data in order to constrain your model, which we have. Otherwise, and you can do this on your own, you can come up with just any number of solutions, which in the end would not be very helpful unless you had some constraints in the model. So the next time we're going to go through a demo. We'll bring up IX1D, and we'll just go through the development of the model for sounding number 3, which is shown here. You can see the base model, which comes up, the default model, is really way off. We can see that there's a in terms of the horizontal dipole, there's an increase in apparent conductivity, and then a decrease. And we can see similar behavior in the vertical dipole, starting off high, going low, coming up high, and then going low again. We could guess that there's a 4-layer model involved. But we'll bring up IX1D and go through the details of assembling your model in the next video. Hope to see you then.